Alright, this is like my 5th time re-recording this. This is not as easy as it seems, man. Alright, I gotta make sure I have what I want to say, on the tip of my tongue. Alright, so let's look at Leetcode 864, shortest path to get all keys. So I'm not gonna actually walk through any code, but I'm gonna just try to explain the algorithm as best I can in plain English. So I feel like if you can understand the intuition behind how to do it in English, then implementing it in code shouldn't be too hard. But okay, yeah, let's get started. So the question is as follows. So we're given a 2D grid and our starting point is this @ symbol. These periods represent cells that are walkable, so that means we can walk on these cells. A hashtag means we have a wall here, so we can't walk on that cell. And then lowercase letters are keys and uppercase letters are locks. So our goal here is to traverse the grid and find all the keys in the shortest number of steps possible. And in this example here, our best path is to go to the right, go to the right, go to the right. So here we pick up the key, the A key, and later we can use that when we keep traversing. Once we come across this lock, since we have the corresponding lowercase letter key, we can open the lock and pass through to get to the other side. So we keep going until we hit this B, right? So if we were, let's say if we wanted to go to the right and then go down and then hit this B here, there's no reason to be going to the right at this crossroads, but just hypothetically we wouldn't even be able to open this B because we don't have the B key for it. Alright, so our goal here is to traverse in some sort of route where we pick up the keys that will allow us to cross through the locks that we need to cross in order to find the shortest path. And so first of all, we need to do one initial pass in order to first see how many keys there are total, because otherwise how will we know once we've how would we know when to stop traversing? So in our first pass we have to first count the number of lowercase letters, so that'll be our key count, right? And then once we actually do our actual traversing, then we can accumulate a current number of keys, and then once our current number of keys reaches our key count, then that means we've found all the keys and we should stop traversing. And so also in the first pass, it's not guaranteed that our starting point will be at this 0, 0 index. So actually in the first pass, since we're looking at all the cells anyways, we can just we can record which cell the starting cell is supposed to be at. And the reason we need to do that is because we need to on-queue something into our queue in order to get the ball rolling, to have like an entry point into to start searching the grid. So if you guys have done any other sort of breadth first search types of problems, this is a pretty standard breadth first search grid algorithm where we kind of just have a queue and then we on-queue all 4 directions. Obviously it has to be a valid index, right? You can't go out of bounds and stuff, and you don't want to be on-queuing any hashtags as well. So pretty much it's a pretty standard breadth first search algorithm. And the reason you want to use breadth first search on these kinds of well, I guess in this particular grid problem is because when you find the shortest path, with a breadth first search you can count the number of steps you've taken level by level, whereas with depth first search you kind of depth first search searches in a way where you first explore one specific path all the way until it reaches like a roadblock or something, right? So that individual path will have its own step count, whereas a breadth first search, everything is kind of synced up, right? Like, let me give you an example. If we're at this 0th step here, we're at the starting point. The first step is these 2 valid cells, right? And then the first step is all the valid cells that we can reach from the first step. right? Which would be this cell, this cell, this cell. So all these 3 cells that I just highlighted, those would be the second step. So you can see how we're keeping track of the number of steps in sync, and in that way, the first time we find all the keys, we can just immediately return that number of steps. Whereas, if you're doing a depth first search, maybe the first time you find all the keys, it might not actually be the best option. There might be other routes that you haven't even started exploring yet, which could be a better, a shorter path. So yeah, so with a breadth first search grid type of algorithm, you should keep a visited set as well. And the idea behind the visited set is just that you don't want to be infinitely looping between 2 certain cells, right? So let's look at, if we started at 0, 0 and we on-queued all the valid cells, right? We would just on-queue 0, 1, right? And then once we're at 0, 1 here, a valid cell would be to go backwards, to go back into the 0, 0 cell, the starting point, right? But that would be pointless. We'd just be looping back and forth infinitely between these 2 cells. So that's just a waste of time. That's not going to help us achieve, finding the rest of the keys. So typically in a breadth first search algorithm, we would mark whatever we've already visited and put it into the visited set. Basically how you would denote that is just, you would have like a tuple, and then have the ij coordinate, and then just put it into a set. And so I'll mention later that in this problem, that's not enough for the visited set. We actually have to take into account a third variable in each visited tuple. We can't just look at the ij coordinate. We also have to take into account our state. And so I'll explain that later. That's what makes this problem hard compared to other breadth first search grid algorithms. And so yeah, so let's take a look at this last example down here, right? So this is actually the one that gave me a lot of trouble when I was doing this. And so essentially, let's just take a look at the best optimal approach to finding all the keys here, right? So we have a key of E, we have a key of B, we have a key of F, key of D, key of C, and a key of A. So once we've collected all of those keys, we can say that's our shortest path. So let's actually look at the shortest path, right? So either we can go to the B here, or we can first go to the E. It doesn't really matter. Either way, we're gonna have to revisit some cells that we've already visited. So like I mentioned earlier, typically you don't want to revisit the same cell again if you've already put it in the visited set. But in this problem, so let's see why you would actually need to revisit a certain cell more than once, right? So the best approach, we can go B, then come down here, and then get the E key, and then we go back over here to pass the E lock, then we go get the F, then we come up to get the D, then we pass back again to F, pass back again to this E, and then come down and then get the C key, and then we can go left or go down, doesn't matter, and then get the pass through the F lock, and then get our final A key, right? So along this path, we revisited several cells that we had already initially visited. But let me start off with the first time we revisit a cell, right? So the first time we revisit a cell, let's say we get the B, let's just start from scratch again. We get the B from the starting point, we get the B, we come down here, and then we get the E, right? And then once we have the E, we have to come back again. We have to cross this cell again, right? But the reason we can cross this cell again is because we've picked up a new key. So the first time we came to this cell, we had only picked up a B key. So what we can do in our visited set is we can denote this by saying we visited the cell 1, 3. This is the cell 1, 3 with the state of just one B key. Right, we can use a string and then just keep appending to this string all the keys that we find. So then the second time around, So, the first time we're here, then we get the E, then we come back here a second time. It's still the same location, but we've come here with a different state. And what I mean by state, like I've said, is we have two keys now, right? We have the B and the E key. So if the state changes, then we should be able to look at this key. We should be able to look at this location again, because these are two different tuples that we're putting into our visited set. However, if we were to, let's say we're here, right? Let's start from scratch again, right? So we go to the B first, and then we come here for the first time. Once we're here for the first time, we don't want to revisit the B that we just came from, right? That would be pointless, because then we would just start infinitely looping. But if we had a different state, then we could go back to the B again. And so so you have to make that distinction. You can only revisit a cell if you're coming to that cell with a different key string, right? This is our key string, which is our state. If you have a different state, you can come back to this cell again. Otherwise, if the state did not change, then you should not be going past this cell again. So that's the key trick here for this problem. And so there's another test case where you'll actually have to pass through the origin again, right? So I guess you have to account for that as well. So maybe that would just fall under the case of having a different state as well. So yeah, you just don't want to be passing the origin if you have the same state. But if you have a different state, then it'd be okay to pass the origin as well. So those are just some things to consider. Let's see, how long has this been so far? This has been 12 minutes. All right, so I guess that's the general gist of it. I mean, I don't want to actually go into writing the code, because I feel like if people look at the code, then they'll be too reliant on just trying to memorize the lines of code. I think it's better if you can just really grasp what you have to do in English, in an English algorithm, and then you'll be able to implement it pretty easily. So I think that's pretty much all there is, all I have to say about this problem. It says return the lowest number of moves to acquire all keys. If it's impossible, return -1. So basically, if you've explored all the options of all the things that you've put onto the queue, that means like at the end, like maybe if all the possible neighbors that you want to on-queue have already been put in the visited set, then then there's absolutely no options left to traverse. Then you would just output -1. Yeah, so the reason I'm doing this problem in the first place is because I actually legitimately saw this in a TikTok online assessment, and it wasn't the exact same problem, but there was some variation to it, and it was very tough. I actually could not get it, and even though I had studied this exact problem on Leetcode before the online assessment, I still struggled with the variation of it on the actual assessment. So hopefully you guys learned something in this video. If you actually want me to implement the code next time and then walk through the line by line of what each line of code is doing, I could do that, but I mean, ideally I want you guys to be able to just try that on your own, because that itself is another I guess that's also another good learning experience, if you can just take what I've said here and then turn it into code. So that'll help you grasp the problem even more, as opposed to kind of just visually memorizing the lines of code and like where the indents are and stuff. It's better for you to recall what I've said, so that you can kind of just work with what I've said in English and put it into code. So yeah, if you guys have any other questions you want me to attempt, I'll try to keep it only to Leetcode hards. I think there's, unless there's like some tough mediums that don't have many resources online, then I can try my best to explain some of them. So yeah, that's about it. Hope you guys learned something. Yep.